Okay, so it is a well-known fact that in dimensions 3 or more, Brownian motion is always transient. With Miha Bresar and Andrew Wade, we consider an analogous question for a reflected Brownian motion in unbounded domain and ask whether it can be stable, and if so, what is the rate of convergence to stationarity. Okay. In order to discuss this in more detail, I need to tell you about what kind of domain, unbounded domain, I have in mind, and we work in the simplest possible unbounded domain in Rd plus 1, which is unbounded in some sense only in one direction. It is described by the scalar function b, which tells me the boundary in this direction x, and in all the remaining directions we take something that is spherically symmetric. Okay, so the process we consider is a reflected diffusion. So this process is diffusive in the interior. It's a martingale in the interior. This W is a d plus 1 dimensional standard Brownian motion. Sigma has to be uniformly elliptic. And this vector field phi, this term is only active when z is at the boundary, because this is a local time term. Local time only increases when z is at the boundary, and it's pushed back, the process pushed back into the interior when via this vector field phi. Now, there are these very general and sensible assumptions that guarantee existence and pathwise uniqueness of this process. This was done in such a domain. We studied that in this paper with Andrew and Misha Manchikov. But there in that paper also we showed that explosions can happen if the reflection is asymptotically oblique. Okay. But the model exists under these sort of simple regularity assumptions. But what I want to know about is whether, if I have a normal reflection, what the long-term behavior of the process is, or close to normal, right? And for that, I need to make some asymptotic assumptions on the behavior of this domain. In particular, I want this b, the boundary b, not to grow too fast. Okay, so its derivative needs to go to 0, and it has to be sublinear. You see, x b dashed goes to 0, x b dashed is sublinear, and it's all proportional to b with a proportionality constant smaller than 1, right? Because it's 1 or more, then it's linear or superlinear, and the process doesn't interact with the boundary sufficiently for the boundary to change the long-term behavior. Because remember, this z has no drift in the interior, right? And I still want it to be positive recurrent. Okay, another thing that I need is that I need it not to die asymptotically to stabilize, so the x direction variance sort of stabilizes at some level, and the remainder variance of the y directions also stabilizes. Okay, and then finally the vector field has to be asymptotically normal, which means that the projection of the vector field as x goes to infinity onto the x direction, ex is this unit vector in the x direction, needs to vanish at the rate b dashed of x times some constant s naught, positive constant. If this was a normal, this s naught would be 1, right? In the y direction, it has to be more and more sort of normal, so we assume that it converges to some c naught, right? In the case of a normal reflection, this would be again equal to 1. Okay, that's easy to see. So under those assumptions, we show in this very recent work that explosions do not occur, and in fact the process sort of grows. It has diffusive behavior in terms of moments. Okay, and this turns out to be important in order to analyze recurrence of this process. Okay, but now, okay, to go to the meat of the paper, we want to know first of all recurrence transience characterization in this context. And it turns out that the critical exponent is beta critical, which is a quotient of these projections, asymptotic projections of the vector field onto x and y directions, as well as the asymptotic instantaneous variances of the process. Okay, so this is some number, this is a non-negative number. And if this non-negative number is smaller than 1 in the interval beta critical to 1, then the growth rate of the boundary. See this beta, I forgot to say on the previous slide, but beta, really you should think about b of x as x to the beta for large x, right? So that's how it behaves. And so if this beta is between beta critical and 1, then the process is going to be transient. If it is below beta critical, minus infinity to beta critical, then the process is going to be recurrent. The boundary case can also be handled with some additional assumptions. Okay, so this generalizes the theorem of Pinsky, who considered domains of this type only for beta non-negative,
which is an important restriction, it turns out, because the interesting behavior happens for negative betas also, in particular the positive recurrence. And in that case, beta critical is 1 over d. You can see that, right? Because this is normal reflection, which means C0 is S0 is 1, and sigma 1 squared is the x direction variance is also 1, and this guy is that trace, so it's just d, right? So it is this, but of course, our theorem tells us that in arbitrary dimension we can have recurrent processes with beta critical arbitrarily close to 1. So for large betas, right? If you're willing to change a little bit the asymptotic behavior of the reflection, if it's not exactly normal, or if you change the ratio of the covariances. Okay, so this is what this process looks like. A simulation. This is a 2-dimensional simulation, okay, with beta critical 0.5. So this is normal reflection, and in the interior, in the x direction, the variance is 1/2, and in the y direction, the variance is 1. Okay, so you can take that matrix, constant matrix like that. You will see a process like this. For beta is 0.65, and this boundary is x to the 0.65. Right? And you can see the way to read it is from dark to bright colors. You start somewhere here and behaves like a martingale in the interior, and then when it touches the boundary, it sort of moves further out. It moves further out, goes out. See, a thing to note here is that I couldn't have taken here a Brownian motion exactly like in the case of Pinsky, because in that case I only see transience. I see only recurrence, because in that case beta critical becomes 1, and beta has to be smaller than 1 for it to visit the boundary sufficiently to see any interaction. So I only see recurrence, but I wanted a transient picture. Okay. Now, okay, so we have the beta critical is the transition from transience to recurrence. Now, how recurrent is this process? And the answer to that is, of course, can be given in terms of return time. So I take my process Z, I look at the x coordinate, and I start it somewhere far away, and I wait for it to come back below fixed level R. And it turns out that the tails of that can be characterized, and the critical exponent is this guy MC. It's 1/2 times 1 minus beta over beta critical. So you remember, beta smaller than beta critical is the recurrent case. So this guy is always going to be positive, right? Because beta is never bigger than beta critical, it's always smaller. But it can be, for negative beta, it can be arbitrarily big, right? And under our asymptotic assumptions, okay, in the transient case, this is basically just saying that if I start above a level, then with positive probability I will not reach level below. That's how diffusions behave, and this is no different here, right? So this is a known phenomenon from SDs. But the crux of the theorem here is in the recurrent case, when beta is smaller than beta critical, then the tail decays exactly as t to the minus mc, right? T to the minus mc. Okay, we get lower and upper bounds that are matching. This epsilon is this perturbation, which is due to the fact that our assumptions are asymptotic. I do not assume anything other than uniform ellipticity and non-degeneracy on the boundary on any compact set. Everything is asymptotic, so one would expect that the only thing that we can get is the polynomial order, and this we get, and the lower bounds here are very important in what follows. I will try to stress that in this and the subsequent video where I discuss the proofs of these theorems. Okay, now a picture is like this. So I take a normal reflection of a standard Brownian motion, so sigma 1 squared equals sigma 2 squared equals 1, a normal reflection, okay, so this makes me beta critical equal to 1, and I get null recurrence when I take beta 0.1, which is smaller than 1. This is still an expanding domain, but the process is still recurrent, and the critical exponent is 0.45, easy to calculate, so this means that the return times are decaying at the rate of t to the minus 0.45. So in other words, this process, you can see that in this picture, right? So dark is again in the middle, and then it sort of moves around the compact part, and then there's an excursion going out. This excursion will eventually come back, but the recurrence, of course, this is null recurrence, it's slow. It is slower than the scalar Brownian motion recurrence, because there the critical exponent is 1/2, as we know, right? Okay, now the main part, in a sense, that addresses the question that I started with is this theorem, which You see, now I know that below beta critical, I am, for if beta is smaller than beta critical, so if the growth rate is smaller than beta critical, then I'm recurrent. And if the growth rate turns out to be smaller than minus beta critical, then in fact I go from null recurrence to positive recurrence. In which case this critical exponent, which is positive and arbitrarily big because beta can be negative, you see that's the case that is not covered in Pinsky's result. In this case, this can be arbitrarily positive, and then there exists a unique invariant measure, okay, for this process without interior drift, so that means the boundary sort of decays, without interior drift, it has an invariant measure, and the rate, the tail, is given as r to the minus 2mc, and we have both lower and upper bounds. Of course, this is harder to obtain than this. And from these lower and upper bounds, we can also obtain the rate of convergence of total variation, okay, which is half the rate, half the tail, it turns out. Okay. Again, there is this epsilon as before because of the no assumptions other than non-degeneracy on compact sets. In particular, what you can see is immediately from this that the stationary measure does not charge the boundary, simply because it's easy to see using occupation times formula that Z does not charge the boundary. Okay, so that's one thing, and another thing is because our lower bounds and upper bounds are matching, we get up to logarithmic terms the exact limit. Okay, for everything. I have a simulation here, so this is beta critical is 1, so because this is just Brownian motion with normal reflection. Okay, and the decay rate is so this is x to the minus 1.2. That's the rate of decay of this function. Okay? And you can see here, you go from dark to bright colors. We start somewhere here, and the process sort of explores the state space, goes out, but then it will come back into the thing. So the tail measure the tail is still quite heavy because of this MC calculation, capital MC, and the total variation converges at this rate. Right. So how does one understand? How can one understand? Put this in some sort of context. So in Pinsky's paper that I mentioned earlier, there is a nice heuristic that tells one heuristically how local time grows. You see, the growth of local time is everything in this context because it is that sort of drives. That's the only drift that the process can get. However, the proof, of course, doesn't do that at all. I mean, it's very hard to control local time. In fact, this is something we do not know how to do. The proofs circumvent this problem. But as far as the heuristic is concerned, it's a very good approach, right? If you know the heuristic for the growth of local time, you can get heuristically that x component of z for large x will behave like this SDE with this critical drift and coefficient beta over beta critical. Now, what is this SDE? This is one-dimensional Brownian motion here, right? So this is for positive beta, this is asymptotically Bessel-like, as one would expect. For negative beta, this is Langevin diffusion-like with heavy tails because the drift is vanishing. Of course, there will be sub-exponential tails. If the domain is asymptotically flat, then this is Martingale-like, and in that case, the return times in the form of return times, this is 1/2 independent of all other parameter values, so it's always as recurrent as one-dimensional Brownian motion, where the critical exponent is also half. Now, how does one prove that? Well, Lyapunov functions have been used in the past to understand stationary distributions of reflecting Brownian motion, like Sarantsev has a paper in 2017 doing that, for example. And there he considers a case with interior drift pushing you towards the compact part of the domain of the wedge, and obtains upper bounds using sort of Markov chain methods, continuous time Markov chain or Markov process methods for obtaining upper bounds. But this interior drift, of course, makes the thing very, very different than in our case, because it makes the stationary measure have much, much thinner tails. They're certainly not polynomial, they're in fact sub-exponential in this case, if I remember correctly. And this interior drift somehow dominates the calculations. We don't have an interior drift, we have a martingale in the interior. So just to recount the novelties of our approach, we look at cover all behaviors, transients to stability in any dimension without interior drift, it turns out. This process does. it's a single class of Lyapunov functions that covers all non-critical cases. I will say something about that in the follow-up, in the second part of this presentation on the proofs. And must be stressed, of course, that the lower bounds are, of course, the hard bit, and these lower bounds need to be set up in such a way so that they match the upper bounds. I will explain how this is done in the second part of the presentation on this topic. I suggest you watch it if you're interested in that kind of thing. But if you're really interested in detail, so you can always look at the paper on the archive. Thank you very much for your attention.